Welcome! Today, we'll dive into an exciting problem from LeetCode, number 1353, maximum number of events that can be attended. Together, we'll explore the challenge, discuss approaches, and walk through the key concepts. Let's get started. In this problem, you're asked to determine the maximum number of events you can attend, given a list of events. Each event is represented as a pair, start_i, end_i, where start_i is the day the event begins, and end_i is the day it ends. The key constraint is that you can only attend one event per day, and each event can only be attended exactly once. Your goal is to maximize the number of events attended. The input is a list of events, where each event is defined by its start and end days, and the output is an integer indicating the maximum number of events you can attend. Let's explore some examples to understand this better. In the first example, the input is 1, 2, 2, 3, 3, 4. Here, you can attend event 1 on day 1, event 2 on day 2, and event 3 on day 3. This allows you to attend all 3 events, so the output is 3. Notice how the events are attended sequentially, 1 per day, ensuring that the maximum number of events is covered. Now, consider the second example, where the input is 1, 2, 2, 2, 3, 3, 3, 4, 3, 4. In this case, you attend event 1 on day 1, event 2 on day 2, event 3 on day 3, and event 4 on day 4. One of the events that ends on day 4 is skipped, as you can only attend one event per day. Despite this, you still manage to attend 4 events, so the output is 4. This example highlights the importance of selecting events carefully to maximize attendance. In the third example, the input is 1, 4, 4, 4, 2, 2, 3, 4, 1, 1. To maximize attendance here, you start by attending event 5 on day 1, event 3 on day 2, event 4 on day 3, and event 2 on day 4. Event 1 is skipped, but you still manage to attend 4 events. The constraints of the problem ensure that you must consider edge cases, such as handling up to 100,000 events efficiently. For example, if all events overlap, you can only attend one. On the other hand, if no events overlap, you can attend all of them. This problem challenges you to design an optimized solution to handle a variety of scenarios within the given constraints. To tackle this problem, we first consider the brute force approach. The idea here is simple. For each day, we examine all the events that include this day in their range, from their start day to their end day. Among these, we choose one event to attend, ensuring that no event is attended more than once. While this method is straightforward and easy to understand, it has significant drawbacks. Specifically, it requires checking overlapping events repeatedly for every single day. This results in a time complexity of O and *m, where n is the number of events and m is the maximum range of days across all events. Additionally, it operates with O1 space, but the inefficiency in processing makes it unsuitable for large inputs. To overcome this, we explore an optimized approach using priority queues, which takes advantage of a greedy strategy. The key insight here is to always prioritize attending the event that ends the earliest and is still feasible to attend. This ensures that we leave as many days as possible open for future events, making this approach far more efficient. Now, let's break down how the optimized priority queue approach works in detail. The first key observation is that attending events with earlier end days first allows more flexibility for scheduling other events later. To facilitate this, we begin by sorting all the events based on their start day. Then, we use a min-heap, or priority queue, to keep track of the end days of events that are available to attend on any given day. On each day, we add all events that start on that day into the heap. At the same time, we remove any events from the heap whose end days have already passed, as they are no longer available. From the remaining events, we attend the one with the earliest end day, which is always at the top of the heap, and increment our count of attended events. This approach has a time complexity of O n log n, where sorting the events takes O n log n, and each heap operation, whether adding or removing an event, is logarithmic. The space complexity is O n, since the heap can hold up to all events in the worst case. Alternatively, we could also use a greedy iteration approach by sorting events by their end day and tracking attended days with a Boolean array. While this avoids the overhead of maintaining a heap, it comes with its own drawbacks, such as requiring additional space to manage the Boolean array. The alternative greedy iteration approach, while straightforward, has some limitations. Specifically, its time complexity is O and *m, where m is the maximum range of days across all events, and its space complexity is O, m, due to the Boolean array used for tracking attended days. This makes it less efficient, particularly in scenarios where the range of days is very large. After evaluating these methods, the chosen strategy is the optimized priority queue approach. This method strikes the right balance between time complexity and implementation efficiency. The greedy principle of prioritizing events with earlier end days is the cornerstone of this approach, as it ensures maximum flexibility for scheduling other events. Sorting the events by their start date further simplifies the scheduling process. We opted not to use the brute force approach due to its computational expense and redundancy, especially for large inputs. Similarly, the greedy iteration with a Boolean array is less scalable for inputs with large day ranges because of its high space complexity. Therefore, the priority queue strategy stands out as the most efficient and practical choice. Every approach has its trade-offs, and the priority queue method is no exception. While it offers optimal efficiency with a time complexity of O and log n, its implementation is slightly more complex due to the use of heap operations. However, this trade-off is justified by its superior performance on large inputs. On the other hand, the alternative greedy iteration method may be easier to implement for smaller ranges of days, but its space inefficiency makes it less ideal for larger scenarios. Ultimately, the heap-based greedy solution emerges as the most optimal and scalable approach for this problem. It provides an elegant way to maximize the number of events attended while maintaining efficiency for large datasets. By combining the principles of sorting, heap operations, and a greedy strategy, this method ensures that we can handle even the most challenging inputs effectively. To solve the problem of finding the maximum number of events that can be attended, we start by organizing the input. Each event is given as a pair, start_i, end_i, where start_i is the first day the event is available, and end_i is the last day. Once we have this representation, the next step is to sort these events by their ending day, end_i. This sorting is crucial because it allows us to prioritize events that finish earlier, maximizing the chance to fit more events into the schedule. If two events share the same ending day, we sort them by their starting day, start_i, to maintain a consistent order. After sorting, the algorithm iterates through each day from the earliest starting day across all events to the latest ending day. During this iteration, we use a set to keep track of the days that have already been attended, ensuring no day is double booked while checking for available slots to attend events. Once the events are sorted, the algorithm focuses on attending as many as possible. For each event, start_i, end_i, we check if there is any day d within the range, start_i, end_i, that has not already been attended. If such a day is found, it is added to the set of attended days, and a counter for attended events is increment. This ensures that each event is considered in order of its earliest possible attendance. The process continues until all events have been checked or there are no more available days left in the range. Finally, the size of the set gives the total number of unique days used to attend events, which directly corresponds to the maximum number of events that can be attended. This approach effectively balances the constraints of scheduling by prioritizing early ending events and ensuring no overlap in attended days. The algorithm hinges on three key insights. First, sorting events by their ending day, end_i, ensures that we prioritize earlier ending events, which leaves more room for others that may finish later. This is a classic greedy strategy to maximize the number of non-overlapping events. Second, the selection process for days is also greedy. By always choosing the earliest available day within an event's range, we minimize conflicts and maximize the utilization of available days. Third, using a set to track attended days is both efficient and effective. This data structure allows for O1 lookups to check if a day has already been attended, ensuring that we avoid duplication. In terms of data structures, we use a list to store the events, which is sorted by end_i for efficient processing, and a set to track attended days, providing quick and reliable checks for availability. The core operations in the algorithm include sorting the events and selecting days for attendance. Sorting the events by their ending days, end_i, has a time complexity of O, n*log, n, where n is the total number of events. For day selection, we iterate through the range, start_i, end_i, for each event and check whether a day is available in the set. This operation has a time complexity of O, n*k, where k is the average range of days for each event. Combining these, the overall time complexity of the algorithm is O, n*log n, plus n*k. In terms of space complexity, the set used for tracking attended days requires O, n, space, as it stores at most one day for each event. This makes the algorithm efficient in both time and space, even for larger input sizes. The algorithm handles a variety of edge cases effectively. For heavily overlapping events, it ensures that the event with the earliest ending is prioritized, leaving more room for the remaining events. For events with large ranges, the greedy approach selects only one day within the range, avoiding unnecessary conflicts. Single-day events are naturally handled as they occupy exactly one day, which is either available or already taken. Lastly, if the input list is empty, the algorithm correctly returns 0, as there are no events to attend. These considerations make the solution robust and applicable to a wide range of scenarios, ensuring accurate results in all cases. To understand the algorithm in action, consider the input events 1, 3, 2, 5, 3, 4, 4, 6. First, we sort these events by their ending days, resulting in 1, 3, 3, 4, 2, 5, 4, 6. Next, we iterate through the sorted events to select days for attendance. For the first event, 1, 3, we attend day 1. For the second event, 3, 4, we attend day 3. The third event, 2, 5, is skipped because day 3 is already used. Finally, for the fourth event, 4, 6, we attend day 4. In total, 3 events are attended, and the maximum number of events that can be attended is therefore 3. This example illustrates the algorithm's strategy of prioritizing earlier ending events and using a greedy approach to select available days. To solve this problem, we start by importing the Heap library, which we'll use to manage a min heap. Then we define a class solution and its method maxEvents. The first step inside the method is to sort the list of events based on their start times, which allows us to process them in the correct order. Next, we initialize a min heap, which will help us track the events by their end times. This is crucial because we want to attend the event that ends the earliest. To determine the range of days we need to consider, we calculate the maximum end time of all events, using the max function. Additionally, we set up two variables, I, which serves as a pointer for iterating through the sorted list of events, and attended, which will count the number of events we successfully attend. Now, we begin iterating over each day from 1 to the maximum day. For each day, we first add all events that start on the current day to the heap by comparing their start times. These events are pushed into the heap based on their end times, ensuring the heap always contains the earliest ending events at the top. After that, we check the heap and remove any events that have already ended before the current day, as those are no longer valid options to attend. Once we've removed any expired events from the heap, we check if the heap still contains any events for the current day. If it does, we attend the event that ends the earliest, which is always at the top of the heap. To do this, we simply pop the top element from the heap using heap.heapPop. We then increment the attended counter to reflect that we successfully attended one more event. Finally, after iterating over all days, we return the total number of events attended, stored in the attended variable. This approach ensures that we maximize the number of events attended by always prioritizing events that end the soonest, while efficiently managing the heap to discard invalid options. This completes the implementation of the solution. Here, we begin by importing the necessary utilities and creating a class called solution with a method maxEvents. The goal of this method is to determine the maximum number of events that can be attended. First, we sort the input array of events based on their start times using arrays.sort. This helps us process events in chronological order of their starting days. Next, we initialize a priority queue, or min heap, which will help us track the end times of events. This is key because we want to prioritize attending events that end the earliest. We also calculate the maximum day we need to process by iterating through the events array and finding the largest end day among all events. This ensures we only iterate through the necessary range of days. Afterward, we set up a pointer, I, to traverse the sorted events, and a variable, attended, to count the number of events attended. Now, we use a for loop to iterate over each day from 1 to the maximum day. For each day, we add all events that start on that day to our heap by checking if their start day matches the current day. This allows us to dynamically track which events are available to attend as we move through the days sequentially. Once we've added the relevant events to the heap for a particular day, the next step is to remove any events that have already ended before the current day. We do this by checking the top of the heap, which always contains the event with the smallest end time, and removing it if its end day is less than the current day. This ensures that our heap only contains events that are still valid and can be attended. Now, if the heap is not empty, we attend the event that ends the earliest, which is at the top of the heap. We simply remove it from the heap and increment our attended counter. By doing so, we maximize the number of events attended while adhering to the chronological constraints. Finally, after iterating through all the days, we return the total count of events attended. This approach ensures an optimal solution by prioritizing events with the earliest end times and efficiently managing overlapping events using the heap. Here, we are looking at a simple case where the input events are 1, 2, 2, 3, 3, 4. The first step is to sort these events by their start time, which in this case doesn't change the order since they are already sorted. We then initialize some variables, min_heap to keep track of event end times, I as the index for the events, attended to count the number of events attended, and max_day, which is the last day any event ends, in this case, day 4. From day 1 to day 4, we evaluate which events can be attended. On day 1, we add the event that starts on this day to the heap, so min_heap becomes 2, as it stores the end time of the event. Since no events have expired, we attend the event that ends earliest, which is popped from the heap, and increment attended to 1. The heap is now empty, and we move to the next day with I updated to 1. On day 2, we add the event starting that day to the heap, making min_heap equals 3. Again, no events have expired, so we attend the earliest ending event, incrementing attended to 2, and clear the heap again. The process repeats as we progress through the days. On day 3, we add the event starting on this day to the heap, so min_heap becomes 4. There are still no expired events, so we attend the event that ends earliest, popping it from the heap and increasing attended to 3. At this point, the heap is cleared, and I is updated to 3. On day 4, there are no new events to add, and since there are no events in the heap, we simply move on without attending any events. This concludes the iteration, and the final output is 3, indicating that we were able to attend 3 events in total. This example demonstrates how the algorithm ensures that we prioritize events with the earliest end times while adhering to the constraints of the given days. Now, in the second example, the input events are 1, 4, 2, 3, 2, 2, 3, 4. After sorting them by start time, they remain in the same order. We initialize our variables again, and empty min_heap, I at 0, attended at 0, and max_day is 4 since the latest event ends on day 4. Starting from day 1, we add the event beginning on this day to the heap, so min_heap becomes 4. With no expired events, we attend the earliest ending event, popping 4 from the heap and incrementing attended to 1. The heap is now empty, and I is updated to 1. On day 2, we add 2 events starting on this day to the heap, one ending on day 3 and another ending on day 2. Since the heap organizes by end time, it becomes 2, 3. No events have expired, so we attend the earliest ending event, which is the one ending on day 2. After removing it from the heap, attended increases to 2, and the heap is left with 3. We then update I to 3 as we continue to the next day. On day 3, we add the event starting on this day to the heap, so min_heap becomes 3, 4. Again, there are no expired events, so we attend the event that ends earliest. Popping the event with an end time of 3 from the heap, we increment attended to 3. The heap now contains only 4, and I is increment to 4. On day 4, no new events are added to the heap. With no expired events, we attend the only remaining event in the heap, which ends on day 4. After popping it from the heap, attended increases to 4, and the heap is cleared. This concludes the iteration, and the total number of events attended is 4. This example highlights how the algorithm handles overlapping events efficiently by prioritizing those with earlier end times even when multiple events start on the same day. In this final example, the input events are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. After sorting, the order remains the same, and we initialize the variables, and empty min_heap, I at 0, attended at 0, and max_day is 5 since the last event ends on day 5. Over the course of days 1 to 5, each day presents a single event that starts and ends on the same day. On each day, we add the event starting on that day to the heap, resulting in the heap containing only one event per day. Since no events expire, we attend the single event in the heap, popping it and incrementing attended by 1 each day. By the end of day 5, attended reaches 5, reflecting that all 5 events have been attended. The output is therefore 5. This example demonstrates how the algorithm handles non-overlapping events where each event can be attended due to their isolated time frames. To analyze the time complexity of this solution, we start by looking at the sorting step. Here, the events are sorted based on their start time using the Python sort function, which operates with a time complexity of n log n. This is because the sorting algorithm compares and rearranges each of the n events. Next, the algorithm iterates through all the days from day 1 to max_day, which is the latest possible end day for any event in the input. Let's call this value d. Since the loop runs once for each day, this contributes d to the time complexity. These two initial steps form the foundation of the algorithm's runtime performance. Now, let's focus on the processing of events, which involves managing a min heap. For each day, the algorithm adds the n times of events starting on that day into the heap. This insertion operation takes log k time for each event, where k is the number of elements in the heap. Across all days, each event is added to the heap exactly once, which results in a total complexity of n log n for all insertions. Additionally, the algorithm removes events from the heap whose n times are earlier than the current day. Since each event can only be removed once, this also contributes n log n in total. Finally, attending an event involves removing one event from the heap, another log n operation. Again, since each event is attended at most once, this step also falls under n log n. Combining these components, the overall time complexity of the algorithm is dominated by the sorting step and the heap operations, resulting in n log n. The d from the day iteration step is bounded by n in the worst case, so it does not exceed the dominant n log n. The space complexity of this solution is determined by 3 main components. First, the min heap, which is used to store the n times of events. In the worst case, all n events could overlap, causing the heap to hold all n elements at once, contributing n to the space complexity. Next, the input list of events also requires n space, as each event is represented as a pair of integers. Lastly, the algorithm uses a few auxiliary variables, such as pointers and counters like I, attended, and day, all of which require constant space, or O1. When we combine these components, the space complexity is dominated by the heap and the input storage, resulting in an overall space complexity of n. To understand the efficiency of the optimized solution, it's helpful to compare it with a naive approach. In a brute force method, you would check every possible day for every event to determine if it can be attended. This involves iterating through all days for all events, resulting in a time complexity of n*d, where n is the number of events and d is the range of days. In scenarios where d is proportional to n, such as when events span consecutive days, the naive approach could degrade to n squared. The optimized solution, on the other hand, uses sorting and a min heap to efficiently manage events. By focusing only on the relevant events for each day and prioritizing events that end sooner, the time complexity is reduced to n log n. This significant improvement is due to the use of sorting and the efficient operations of the heap. Now let's summarize the best, average, and worst-case scenarios for the algorithm's performance. In the best case, all events are non-overlapping, meaning the heap will contain at most one event per day. Even in this scenario, the sorting step still dominates, so the time complexity remains n log n. For the average case, we have a mix of overlapping and non-overlapping events, which causes the heap size to vary over time. However, the overall complexity of heap operations still remains n log n. In the worst case, where all events overlap significantly, the heap may grow to its maximum size of n. Even then, the heap operations remain efficient, keeping the time complexity at O, n log n. Mathematically, the pre-processing step of sorting contributes O, n log n, while each event is added to and removed from the heap exactly once, also contributing O, n log n. The iteration over days adds O, d, but since d is bounded by n, it does not exceed the dominant O, n log n. Overall, the algorithm achieves a time complexity of O, n log n, and a space complexity of O, n, making it both efficient and scalable for large inputs. When tackling this problem, there are several common mistakes to watch out for. One major issue is overlooking edge cases, such as overlapping events, events with identical start and end dates, or scenarios where no events can be attended. These situations often lead to bugs or incorrect results. To address this, it's important to test your solution on minimal and maximal inputs, including single-day events and completely overlapping events. Another frequent mistake is using inefficient iteration methods, like nested loops, to check for overlapping intervals or available time slots. This can result in very high time complexity, such as O, n squared, or worse. Instead, you can optimize by sorting or using data structures like heaps to eliminate redundant checks. Sorting itself can also be a pitfall. If you sort solely by the start times of events, you may end up with suboptimal schedules. A better approach is to sort by end times first, ensuring you maximize the number of events attended. Finally, while a greedy algorithm is a common solution, it's easy to make a misstep by not validating the greedy choice for all inputs, especially when event durations vary widely. To avoid this, carefully reason through your approach and test it against counterexamples to confirm its correctness. Another challenge is accounting for time constraints. Misunderstanding the number of days available to attend events or improperly handling multi-day events can lead to flawed solutions. To fix this, you need to carefully track time allocation and ensure your solution respects all constraints. From an interview perspective, this problem is a great test of your ability to apply greedy algorithms, often in combination with sorting or heaps. Mastery of these techniques is critical for solving time interval problems efficiently. Interviewers are also likely to focus on your ability to optimize time complexity, expecting you to move from a naive O, n squared approach to O, n log n, using better algorithms and data structures. Moreover, handling edge cases is another key area. Be prepared to explicitly discuss how your solution deals with scenarios like overlapping events, single-day events, or cases where no events can be attended. Lastly, debugging skills are essential during interviews. You should be ready to explain how you'd verify correctness, particularly under time constraints. To further strengthen your understanding of this problem, it's helpful to practice related problems that follow similar patterns. For example, Meeting Rooms 2 on LeetCode focuses on interval scheduling and determining the minimum number of meeting rooms required. Another problem, non-overlapping intervals, challenges you to remove the minimum number of intervals to eliminate overlaps. Of course, the maximum number of events that can be attended problem itself is a direct variation and great for refining your approach to overlapping intervals. Additionally, interval list intersections explores finding intersections between two lists of intervals, which involves similar concepts of managing overlapping time ranges. Practicing these problems will deepen your understanding and improve your ability to handle interval-based challenges. There are also alternative approaches worth considering for this problem. One of the most effective methods is the heap-based approach, where a min-heap is used to track the earliest ending events. This enables efficient event selection and minimizes the need for full iteration. However, the trade-off is slightly higher memory usage compared to simpler sorting techniques. For variations of the problem that involve maximizing weights, such as event importance, dynamic programming can be a powerful tool. DP allows you to explore all combinations, though it comes with higher time complexity, often O, n squared, or O, n asterisk k, where k represents the number of days. Lastly, you can use binary search combined with sorting to locate the next available event quickly. While this method is a bit more complex to implement, it can lead to significant runtime improvements in certain scenarios. Each of these approaches offers unique strengths and trade-offs, so understanding when and how to apply them is key to solving variations of this problem efficiently. Great job! We've covered the key insights for solving maximum number of events that can be attended. Remember the power of greedy algorithms and prioritization techniques for scheduling problems. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!